hybridization. We're going to get started talking about carbon hybridization more specifically. Touched on it. Let's talk about it some more. So this is essentially section 1.10. Which deals with ethane, ethylene, and acetylene, or ethine. So we're going to look at carbon, three different carbon molecules. Give us a picture here. So let's start with ethane. Ethane is this, 2 carbons. We'll go over naming more specifically later. Two carbons with 3 hydrogens on each carbon. And the way we would view each carbon now is tetrahedral. We drew out methane and showed how it's tetrahedral. Every carbon is going to have wedges, and show these at some point for a lot of carbons, but we'll get used to these wedges and dashes. Again, they have to be adjacent to one another. So that's a picture of tetrahedral carbon here. These carbons are both tetrahedral, sp3 hybridized. We're going to go over this several different ways. These bond angles are all 109.5 degrees. Now, this orbital picture that we introduced last time, we're going to kind of come back to it again. This orbital picture, you would look at it kind of like this. You got these carbons that have sp3 orbitals overlapping, forming a bond. That's the carbon-carbon bond. And all the orbitals coming from carbon are sp3. Remember, there's an anti-bonding orbital. I'm not going to draw it over here. And an anti-bonding lobe over here on each side of the carbon. And so all these sp3s, we're going to use kind of some shading to mimic the wedges and the dashes. And then what's happening is H's are now bound at each of those, bound to the carbon. So it's a H1s with a C sp3 orbital. These are sp3 orbitals. 4 of them, 4 equivalent orbitals, okay? Remember, the S and 3 P's combine to form these. That's an sp3. So the same thing's going on here. You got the sp3 with the H1s, and you got one coming out and one going back behind, H1s, okay? So you got a carbon sp3 bond plus a carbon sp3 bond in the center there. And then you got carbon sp3 H1s bonds. Okay. Again, these 2 representations are different sides of the same coin. A very important point here is that this carbon-carbon bond, carbon-carbon single bonds, can rotate like an axle of 2 wheels or something like that. Think of the carbons as wheels. The wheels can spin on that axle. Okay, so this bond, these carbons can rotate about this bond. That means this CH3 is always moving around and spinning around. I know I just disrupted the view of that, but it's always spinning around, and we'll look at some models. Okay, so that's really important. Carbon-carbon single bonds allow for free rotation. Okay, so that's ethane. Let's look at ethylene, or ethene is actually the IUPAC name. We'll talk about that later, but we call it ethylene, and it looks like this. Remember when we introduced molecular shape, we said the double bonds don't count in terms of the shape. So these bonds are all 120 degrees. This shape is trigonal planar. Okay, the orbital picture, at least one version of the orbital picture, looks something like this. We're going to take this flat molecule, this trigonal planar molecule, and we're going to kind of look at it this way. And so we're going to use wedges and dashes. This is one of the few times we use wedges and dashes on alkenes. This is just to give perspective. These carbons have a sigma bond and a pi bond, we call it. We're showing the sigma bond here. Okay. And I'm going to give you some ways to help remember this. Single bonds are sigma bonds, and they come from sp(x) orbitals. We'll go over this over and over, and you'll see what I mean. But single bonds come from sp(x) orbitals, and they are sigma bonds. Okay, so we're going to use alliteration to help us remember this. Where do pi bonds come from? They come from empty or leftover p orbitals, rather. In the hybridization process, or in the way we understand hybridization, there's a leftover p orbital on each carbon with one electron each. That forms the double bond. Okay? So instead of putting a single electron in one of these lobes and drawing a line, we're going to show dashed lines, which you can think of as sort of a half a double bond is above, and a half of a double bond is below, so you get one whole double bond. And it's all probability of electron density. This is an unhybridized 2pz, let's say, 2pz. And these are going to interact. There's going to be electron density above and below. And it's going to be a double bond. We represent it over here as sigma bond and pi bond. But the pi bond really is electron density above and below. Okay, let's look at an orbital picture of this just to reinforce. We got our two carbons. We've got our sp3 orbitals that are forming a sigma bond. We've got another sp3 orbital going back, bound to an H1s. Another sp3 orbital going forward, coming forward, bound to an H1s. Same thing over there. And same over there. Unhybridized p orbitals. Okay. Now, in contrast to the sigma bonds, the sp3 hybridized, where there's free rotation, this double bond cannot rotate. Carbon-carbon double bonds cannot rotate like an axle. Right, like the axle of a vehicle, we can't do that. Now, this molecule will tumble in space and rotate in space. It'll fly around, but it is not going to spin on the axle. It's a big difference. Okay, so that's ethylene. Let's look at ethine, or more commonly referred to as acetylene, as in an acetylene torch, acetylene gas. This could also be drawn like this, implied car coming up soon. Okay, so the C's will get dropped off. But now all we have is extra unhybridized p orbitals. Okay, this, it's going to look something like, those are all sigma bonds. They're all single bonds. They're all sp orbitals. What's left over when we have sp hybridization is two sets of p orbitals. There's a p orbital on each. Let's call this the pz to be consistent. And then what do we have? We have the px or y, it doesn't matter, in the back and in the front. A lobe in front and a lobe in back. Again, there's electron density. Think of a half bond here and a half bond here, and then a half bond behind and a half bond in front. The net result is there's a sort of a tube of electron density. Okay. There's two pi bonds. Two sets of unhybridized p orbitals form two pi bonds, hence a triple bond. Okay. A double bond is a sigma bond and one pi bond. A triple bond is a single bond and two pi bonds. Again, these orbitals here are sp from the carbon plus H1s. This carbon-carbon is carbon sp plus carbon sp. Let's look at the orbital picture. There's our carbon sp with H1s, carbon sp with H1s. What do we have left over? P, P, similar picture as above. Again, the carbon-carbon triple bond cannot rotate like an axle. It can tumble in space, but it cannot. So it's a tube or a cylinder of electron density. All right, so that is an introduction to those three molecules. Let's look at some examples. A few examples here. And I want you to be able to, I may ask you to draw some orbitals, but they would be not overly complex examples, but I may ask you to draw some orbitals, but I want you to be able to identify orbitals and understand them. So let's draw a molecule in a skeletal type of representation. We've got an alkyne, we call this, the triple bond, and we've got a CH3 group. So we should be able to look at every bond in this molecule and identify if it's tetrahedral, if it's linear, if it's trigonoplanar, if it's the hybridization of atoms, the hybridization of bonds. Okay, so the alkyne is linear. This is tetrahedral, sp3 hybridized, which means this carbon-carbon bond is a C-sp3 bound to a C-sp. Each carbon you have to account for. This carbon hybridized has 2 sigma bonds and then 2 pi bonds. This is an alkyne. It is sp hybridized. So within this bond, there's 3 bonds. There's a CSP, CSP. There's a C P plus a CP, and there's 2 sets of those. So PY, PY, and then CPZ plus CPZ to form the triple bond. Whatever the case is, I'm not asking you to give me Z or Y or X. Okay, I'm asking you to recognize that there are 2 sets of p orbitals there. This bond is a CSP H1s. This bond is H1s CSP3. Okay, so very important that you start to recognize what all these bonds are. Okay, I'll give you a couple take-home molecules to think about. A couple with oxygen in them. Okay, so take those home, think about every single bond and the hybridization. Okay, so now let's review. This is a really important concept, so I'm actually going to go over it twice essentially. Let's review hybridization and what we mean by hybridization. We're taking atomic orbitals, the s, the px, the py, the pz. We're going to mix to form hybrid orbitals. Okay, so let's look at elemental carbon. Sorry. Elemental carbon and sp3 hybridized carbon. Again, we're going to take atomic orbitals. Let's look at the electron configuration of carbon. We're going to ignore this 1s, but I'm going to put it there just to remind you. The 1s is filled. The 2s is filled. We talked about the Pauli exclusion principle, the Hund's rule, etc. And the 2p, again, the valence number of carbon will never change. It's always 4. There are 4 valence electrons. 2 of them are in the 2s, and let's just label these x, y, and z again for arbitrary purposes. 2 of them are there, and they have to fill in degenerate orbitals before they can for a second one can go in X. Okay. Hybridization is going to take again, we're ignoring the 1s because those are not valence electrons. They're core electrons. We're taking the 2s and the 2p orbitals, and we're mixing to give 4 degenerate sp3 orbitals. Why 3? Because you put in 3 p's and 1 s, so therefore there's 4 equivalent sp3. Think of each of these orbitals has 1/4 s character and 3/4 p character, and they're all equivalent. How many electrons? 1, 2, 3, 4. So this is a more sophisticated picture of Lewis structures, right? We went in with carbon with 4 electrons, and we put 4 hydrogen atoms around there with 1 electron each, and we formed methane, for example. Okay. So now, and again, the 1s is still there. There's the 1s. It's core. We don't care about that. We'll ignore that from now on. Now, sp3 orbitals. Always, I'm going to give you some rules. Always form, or always and only form, sigma single bonds. They're incapable of forming double bonds. Okay? So sp3 orbitals only form sigma bonds. And what I want you to remember is single bonds or sigma bonds are formed by spx orbitals. That means sp3, sp2, or sp, meaning sp1. Okay? So these types of orbitals form single bonds. So let's look at sp2 and sp again. And then we're going to look at it from another angle. So sp2, right? We have the same sort of, we're going to take the same orbitals, okay? The atomic orbitals, the s and the three p's, or the 3 sets, the 3 different 2p's, okay? And we're going to get, let's just draw it out. I was going to skip that, but the 2p and the 2s, right? We got 4. It's the same thing every time. Hybridization, sp2 looks like this. What's left over? Let's call it the 2pz. Again, this is 1/3 to 2/3 now. There's more s character. That'll be important later on. Okay, each orbital is 1/3 s and 2/3 p. Why? Because 2 of them and 1 of these mixed, right? Those mixed. This is the 2pz that is not involved in the mixing. Okay, we still have 4 electrons. P orbitals p orbitals are unhybridized or leftover. Unhybridized leftovers. These unhybridized p orbitals always form pi bonds. That's a pi bonds. What do we say? Single bonds, single bonds are sigma bonds. They are formed by spx orbitals. Pi bonds are plus bonds, if you want to call them that. Plus bonds are pi bonds, okay? Double and triple. Plus bonds are pi bonds are formed from p orbitals. All right. Finally, let's look at sp. And again, think of it as sp1. And here's our energy. We got the 2s and the 2p X, Y, Z. Now we're going to hybridize, and we get, now only 2 of them are involved. You're always having 4 electrons, so it's not the number of electrons, it's the type of bond we're looking at. Here, we're talking about sp. Now it's 50-50 s, 50% s, 50% p. What's left over? Let's say the y and the z of the 2p. Okay, still 4 electrons. Each of these electrons here are going to be half of a triple bond. Okay, half of a double bond and a triple bond in an alkyne. And so, and then these are going to form bonds with hydrogen or whatever. Okay, so sp. sp1 orbitals always and only form sigma bonds. P orbitals that are unhybridized or left over always form pi. Again, anytime you see a single bond, any single bond, it is going to come from an SPX orbital. What do I mean by X? You could say SPN. It doesn't matter. SP, there are 3 possible hybridization states that we'll talk about throughout the whole course. N equals 1, 2, and 3. What's N equals 1? SP. It's going to be triple bonds every time. What's N equals 2? SP2. Double bonds. What's N equals 3? SP3. It's the number of p orbitals involved in the mixing. And depending on that mixing, you may have leftover p orbitals. Okay, the number of leftover p orbitals is n. What is it? Whatever. You will have leftover p orbitals. I was going to say something and I lost my train of thought. SP, SP2, SP3. Okay, so my point is that these types of orbitals, one of these 3 possibilities, will always constitute single bonds. Anytime you see a single bond, it's a sigma bond. It comes from an SPX or an SPN orbital. Okay. Anytime you see a double or a triple bond, it comes from p orbitals. All right. So now let's look at these 3 molecules again. We're going to go back over ethane, ethylene, and acetylene. Let's look at those. We have C1 and C2. I'm leaving off the wedges and the dashes, but they're still there. That's a 1. It's a terrible 1. 1 and 2. Remember, we talked about Lewis structures. Now we are going to look at a hybridization or a hybridized view of this. So what do we have? We got our sp3 orbitals, right? We took all the p's and the s's and they mixed for both carbons, and we have 4 degenerate orbitals with 4 electrons. So this is C1 over here. This is C2. Same thing with C2. We have 4 degenerate orbitals. They're sp3. They're equal in energy, and we have 4 electrons. This right here is the central CC sigma bond. This guy. Okay, it's just another picture. It's a deeper reality of that C1, C2 bond. And then where do these 3 electrons go? They go with hydrogens. We have a bunch of hydrogens and they're 1s. These would all be spin opposite of one another. We're not going to worry about that so much right now. H1s. Here's a CH bond. Here's a CH bond. There are 6 of them. We have now accounted for all of our electrons. There were 6 CH bonds over here. Okay, it's really a beautiful convention picture of things here. These are CH. What kinds? Sigma bonds. All single bonds are sigma. There are no pi bonds in this molecule. All right, so that's ethane. That is the orbital picture. Okay. Count the valence electrons. 2, 4, 6, 8, 10, 12, 14. Number of valence electrons should be 14. Go through. I give you C2H6. You should be able to draw all this, honestly. Let's look at C2H4. Okay. You'd come up with a Lewis structure, and it would look like this. That's all well and good. That's a Lewis structure, but we got 12 valence electrons. Let's assign our valence electrons. And again, what you're doing is looking at a double bond and saying, I recognize that this is sp2. And so what does sp2 look like? Looks like this, 3 degenerate orbitals, right? sp2, 1/3 s, 2/3 p. You've got these 3 sp2s. 1, 2, 3. What's left over? The pz, let's call it. 2pz, unhybridized, so you got 4. You got another one over here. This is carbon 1, carbon 2. All right, sp2 orbitals, 3 of them. 2pz. Now, which bonds are which? Here is our C sigma, right? Single bonds, sigma bonds, sp2, okay? The leftover p orbitals form the double bond, the pi bond, C pi, okay? What are these forming? H1s. We got 2 hydrogens, each with a pair of electrons. CH bond, CH bond, CH bond, CH bond, okay? CH sigma bond. Let's do sp. C2H2, 10 valence electrons. You come up with this. Now let's look at the hybridized version view. You got C1 and C2. sp takes an S and a P and mixes. Boom, boom. You got 2 leftover P's for both carbons. Call them 2py, 2pz left over. Still have 4 valence electrons. Again, you look at a triple bond, you know it's sp. Where's the single bond? Right here. C sigma bond is the single bond. It's kind of in the middle of this triple bond. What are these? Well, there's 1 pi bond, carbon-carbon pi. There's the second pi bond that is essentially the triple bond. So there's a double and a triple bond. What's left over? H1s with 1 electron, H1s with 1 electron, forming a CH bond and a CH bond. And you get, that's the picture of the alkyne. Okay. You should be able to draw out for these 3 molecules and distribute these electrons. Okay. All right, so wrapping up this lecture with just a little bit more, 1.11 is bond length and strength. Now that we've looked at the reality of these, let's look at a few trends. Okay. Let's look at carbon-carbon bonds. I want you to remember shorter equals stronger. And remember this principle that electron density is pulled through nucleus. So let's look at some examples. We have carbon-carbon bonds here. .53 angstroms. I am not going to make you list numbers. I want you to understand principles. 1.53 angstroms is the distance of a carbon-carbon bond, carbon-carbon single bond. Doesn't really matter what's attached, but this distance of, and again, we have a sigma bond and a pi bond, but overall it's one thing, okay? The distance of that is 1.34 angstroms. It's shorter, okay? And finally, we have a triple bond. And this distance is 1.21 angstroms. Again, shorter. Okay, so shorter equals stronger. Okay, we can measure the bond strengths by 88 kcals per mole for a single bond, 152 kcals per mole for a double bond, and 200 kcals per mole here. So increasing strength, increasing length. Okay, there, as it increases in length, it gets weaker. As it increases in strength, it gets shorter. Now, a really important thing here, though, these energies represent the amount of energy released, okay, from those bonds. And so that means the strength of those bonds are representative here. Okay, so what we can see is a triple bond is stronger than a double bond, is stronger than a single bond. That makes sense. There's more electron density there. It's harder to break 3 bonds than 1. Okay, but notice it's not completely additive. 88 times 2 is more than 152. It's 176. 88 times 3 is much more than 200. So the take-home message is pi bonds themselves, the double and the triple bonds, are weaker than sigma bonds. Let me say that again. Pi bonds are weaker than sigma bonds. That's the bigger principle here, rather than memorizing bond. Even the trend is important. You should learn that. Okay, but the really important thing is that pi bonds are weaker than sigma bonds. We're going to see this in reactivity a lot. Okay, pi bonds weaker than sigma bonds. Okay, that's worth memorizing. Let's look at CH bonds to reinforce this. Okay. So CH bonds, let's look at a trend. CsP3 bound to an H. We have a CsP2 bound to an H and a CsP bound to an H. This is just what we looked at. Ethane, ethylene, and acetylene. Okay, a single, a double, a triple bond bound to an H. What's the trend here? The bond, it's not a big difference, but it's a difference. 1.11 angstroms, 1.10 angstroms, and 1.09 angstroms. Subtle, but enough. So we have this direction is, that's decreasing length. So I'm going to go the other direction. Increasing length. As the bond length increases, it becomes a little weaker. Okay, so here we have 98 kcals per mole for this CH. We have 104 and 125. Notice it's definitely not additive. It's different. These are different bonds than we're talking about, but we see the CH bond getting a little bit stronger. The way we're going to rationalize that is by the percent S character. Okay. So I want you to memorize something else. S orbitals pull electron density closer to nucleus, or they hold it closer. This makes sense. The s orbital is a sphere. It's not as far out there. It's closer to the nucleus. So the s orbital is going to pull or hold that electron density a little bit closer to the nucleus. So the more s character we have, the more it's going to impact the strength of the bond. Okay. So increasing s character percentage equals increasing bond strength equals increasing bond length. Decreasing, my bad. Increasing bond strength, decreasing bond length. Again, the goal here is to understand the reality of these atoms, not to memorize a bunch of charts per se. You should memorize and use that as a tool, but it's not the ultimate goal. So sp has 1 2s and 2 hybrid orbitals. Okay, we're measuring the percent s character. If it's sp, there's an s and there's a p. It's 50-50, but it's 50%. There's one s among the two. All right, that means 50% s. sp2, you get the idea, is 1 2s. There's always 1 2s. That's is always on the top, and then 3 hybrid orbitals equals what? 33% s. sp3 1 2s divided by 4 hybrid orbitals equals 25% s character. We're going to see this in chapter 2, how s character is going to impact acidity, and so it's important to just kind of start wrapping your minds around this. sp is 50% s, sp2 is 33% s, and then sp3 is 25% s. All right, that wraps up this lecture. We have one more in chapter 1, and we'll finish that up. And next time, it'll be on electronegativity and polarity.